Before we launch into concepts from digital communications such as modulation formats, receivers, transmitters, different strategies for equalization, all of this heart of digital communications, we have to set up a few basic concepts on how we start out with our data. So how is our data? Is it originally analog? Is it digital? What kind of manipulations do we do? So in these sections of the book, we get through some basic concepts that are sort of the starting point as we go into more advanced topics. So the first thing we have to talk about is a little bit of vocabulary. We all know what a bit is, a logical 0 or a logical 1. We can group these bits into a block, which we can call a symbol. So it could be a collection of k bits that would form a symbol. And then we typically have a collection of symbols. So 2 to the k would be all of the possible symbols of length k that could be created, and we call that an alphabet. And we'll be calling that even later maybe a constellation as we look into different kinds of modulation formats. That might be a more appropriate term. So bit, binary, symbol, some collection of multiple bits, and of course eventually we have to transmit this data, and that takes the form of a waveform. And so we'll be looking today in the discussion about two simple selections of how we might transmit a symbol. And then we'll discuss what some choices that we could make, what the implications of those choices are. And then I'm going to end today with a little bit of a case study of a practical example and something that will relate to some of the homework assignments that you'll be looking at. So one concept might be that we have a digital communication system, but the signal that we have to transmit is actually an analog signal. So we know the sampling theorem tells us that if we sample our analog signal fast enough, what perfect reconstruction is possible. Of course, this assumes infinite resolution of the stored sample. And in reality, this may not be the case, that we have to do some sort of analog to digital conversion, and this may have finite resolution, a finite number of bits to represent the analog signal, and it could also be a device, a component which has finite bandwidth. So how quickly we want to sample might be an issue. So this is if we start out with analog signals, and you may think that, let's suppose we're starting out with digital data, then everything is quite simple, and that's not quite accurate either, because when we do our transmission over our communications link, it's true that the data we will be transmitting is digital, because we're talking about digital communications. However, the media is actually transmitting an analog signal. It's either light on a fiber, it's voltage on a twisted pair wire or on a cable, or it's the electric field which is transmitted in wireless. So this means that inside of our transmitter we sort of have to do some sort of digital to analog conversion. And that digital to analog conversion could be a simple analog circuit, or it could be a complex device with a lot of flexibility. And I'll talk about that a little bit more at the end. It might be important because the symbol waveform that we choose, we might want it to be interesting. And when I say interesting, looking for some characteristics that make it more robust to impairments which may come up in a communication systems. And we'll spend some time in the coming weeks to discuss what kind of waveform might be appropriate and interesting. But again, the issues that we'll be coming back to are always finite resolution and finite bandwidth available. So with this in mind, let's think about the sampling even of the analog signals, assuming we started from analog. So here we have a continuous time waveform, and we could do something called natural sampling, where we would just look at the analog signal during certain intervals of time. This could be a symbol interval or a symbol interval, let's say. And we could quantize that level. So now we're looking at the finite resolution of the circuit we might be using. So natural sampling would have any continuous version here, and we would save, if you will, a continuous a real number. But here we're looking at a discrete level, and there might be a certain number of bits which are available. And then we have sample and hold, which would be a typical way of converting them. And so during a given symbol interval, there would be some value which is quantized and which represents our signal. And we'll be looking at an example for this and going on to some other formatting choices that we might make when we convert this analog sampled signal into the digital signal that will be sent. So here's a simple idea of the quantification that we could do to an analog signal. And in this case, we're looking at 8 different divisions of voltage levels, which will be used to quantize this signal. So what we see here is the natural sample value, 1.3 at the first sampling instant, 3.6, 2.3, etc. And this is our analog waveform. And then we can quantize it, and so that we will, even whenever it falls in a certain bin, I will always give it this quantized level. So anything between 0.5 and 2.5, I'm going to assign it the value of 1.5. So here we have the quantized values of our signal in this case. Now the next step is to assign a code number, if you will, to each one of these quantized levels. And in this case, there are 8 different quantization levels, and I can just assign them a name. So there were 8 levels, so I will give each one of the bins that this might fall into a certain code name. So now I have discretized the original signal, and I've sort of, instead of having some real voltage level assigned to it, I sort of abstract this idea and say that there's some code number, and then of course my code book would know that when I see code number 7, that means level 3.5, and so these particular choices can become arbitrary, and our goal as a communications system is to be able to transfer this information, which is the digital information, transfer this into from one point A to point B. So I have 8 levels, and we might say, well, I'm going to use 3 bits in order to transfer the code. And so I'm going to assign a 3-bit sequence to each one of the code numbers. For instance, I could just count in binary from 0 to 7, and each one of the codes would be the binary representation of that code number. Now, this method of transmitting quantized information is known as pulse code modulation. So I just assign a certain number of bits, and here we can clearly quantify the quantization level as 3 bits of resolution. Now, there's another way that I might have transmitted this information. Instead of turning it into a binary signal, I could turn it into a multi-level signal. And in that case, we would call this pulse amplitude modulation. For instance, instead of assigning 3 bits, I could put in a certain discrete level. And for convention, we usually use these odd integers as a representation of the levels we use. So you can see that there's plus and minus 1, which are separated by 2. If I go to another 2, it's plus 3, plus 5, plus 7. So these are just sort of arbitrary reference numbers, which make it easy to count. But in this case, you can see that we have 4 discrete levels, which are going to be used to send information from the quantization. So these are both valid ways of turning analog data, quantizing it into digital data. And what is the implication of these 2 choices that we're looking at? In this example, we'll be looking at 4 level, and perhaps I should have been a little clearer. This is 8 levels of modulation. There's 4 absolute values, but of course there's 8 distinct levels which are going to be transmitted, and those 8 distinct levels are equivalent to this 3-bit representation in a bit. So I could send a symbol which is at plus 7, or a symbol at minus 3, or I could send 3 bits in a row, 1, 1, 1, which is telling me that the level is +7 or etc. So now let me take an example, a specific example, and explain to you what the implication of that is. And I'm going to just simplify it a little. Let's say that there are only 4 discrete levels, and that each of these 4 levels could correspond to some 2-bit sequence. So for instance, here's my +1 level and my +3 level, my -3 level, my -1 level, and there's an equivalence between this +1 level and the bit sequence 1, 1, between the +3 level and the bit sequence 1, 0, etc. So when I quantize my analog signal, I can either send it in this PAM multi-level signal, or I could use a PCM signal where I sent this bit sequence. And they're essentially conveying the same information along our digital communication system. So what is the difference between the choice of pulse amplitude modulation and PCM modulation? So in black here, we see there's 4 levels. And in red, we see there's 2 levels, logic 0, logic 1. But there's another difference. It's not just the value of the voltage. We can see that the transitions are happening much more quickly at PCM modulation than in PAM modulation. And recall, if we have faster transitions from our Fourier analysis, we know that that means that there's greater occupied bandwidth. So we can see, I had the discussion earlier, that there was limited resolution, which could lead to quantization error, but there's also going to be some limited bandwidth in the conversion of our signals, and that would mean that PCM, which occupies more bandwidth, could be more problematic. So we have these 2 choices, and it's good to have 2 choices because we can always make a trade-off when we design a communication systems on which is the most appropriate for a given application. So that's a basic idea, PAM, PCM. We'll be talking about them a little bit more extensively from this chapter. And I want to just give you a little extra reading, which is a little bit more practical. And this will hopefully be helpful for you to start early on to do some reading more broadly that will help you in the small project that will be turned in as a homework assignment. So let me just give you an idea here about digital to analog converters. So we will be discussing pulse shaping. Pulse shaping will be desirable, that when we send this analog signal, a waveform which represents a symbol, certain shapes may be more robust to impairments than other. And we have this idea of the digital level, which is PAM or PCM, but there's also this shaping, and the shaping applies to voltage, to the EM field, electromagnetic field, could be a shape, a waveform, which covers many symbol intervals. So when I develop a symbol sequence that I would like to transmit as my digital data, that I have to convert this into some sort of pulse shape and into an analog signal, which will actually go over the communications media. So eventually I have to create an analog waveform that is going to be transmitted. And I could use that with an analog circuit, or I could use a digital to analog converter. And a digital to analog converter gives us a lot of flexibility in looking for this really desirable pulse shaping, which might be difficult to achieve in an analog circuit. So all that to motivate why a digital to analog converter might be a good tool that we might want to use. So there are a couple of key concepts on the performance of a digital to analog converter. One thing that is of interest is the sampling rate. If I want to send information quickly, of course, I'd have to be able to sample very quickly, and therefore the sampling rate would be a key performance indicator. Clearly, the number of bits of resolution in a DAC will have a big impact. If I'm trying to get a very desirable shape, I want to be able to see those differences in shape, and the resolution in bits are going to permit me to see that. I talked already about the bandwidth. Limited bandwidth is going to impact how fast I can send my information. Effective number of bits is something we see often on a spec sheet for a digital to analog converter or an analog to digital converter. And this is some way of sort of combining those previous ideas of bits of resolution and limited bandwidth into something that combines the two limitations into one figure of merit. Another important characteristic of a DAC would be the output voltage range. Depending on the noise level, if I could have a larger voltage swing, I might be less influenced by the noise. And always in quantization, we typically look at clipping, and clipping is a tool that we can use with the DAC to try and increase the performance. So as I mentioned, effective number of bits is a way of quantifying distortion. Distortion comes from many factors. It comes from limited resolution. It comes from limited bandwidth. It comes from the additive noise, which has to do with that voltage swing. So if I go back here, there are a number of factors which are key indicators for the DAC, and ENOB tries to bring them all together so that I have one number that gives me a feeling for how these three interact together. So I'm going to talk about a DAC which is available in the laboratory, a very high performance MICRAM DAC, which is used in our very high bit rate experimentation. And I hope that during this class I'll be able to let you use, not directly but virtually, be able to submit a pulse shape that you want to have produced by the digital to analog converter, and then we'll see what the waveform looks like and whether it has the characteristics that you're looking for. So that will be a practical exercise that we'll do by the end of the semester, and of course we'll wait and try to pick up some skills along the way before you attack this. But I thought we'd start right off in the first week by looking at some of the documentation which is available for the DAC. So if we look for this particular DAC, there are a number of channels, so we could have multiple channels that could be created. It has about a 35 gigahertz analog bandwidth, very, very wide bandwidth. It has 6 bits of resolution. We'll see on the spec sheets the rise and fall time, the jitter, and the sampling rate of this DAC is extremely high, up to 100 gigasamples per second on each of the available channels. So this DAC has with it a limited number amount of memory, a buffer, if you will, that allows it to send a certain amount of data which can be transmitted. So this is just a summary of the kind of specs that you might look at for a digital to analog converter. And if we look a little bit more closely, we could look, for instance, at the voltage swing which could be achieved, of course also the number of bits of resolution, and all of this are going to contribute, as I said, to the effective number of bits. So although we said there were 6 bits, because of the limited bandwidth, the limited swing, it's kind of like the equivalent of 4.5 bits when I'm trying to operate this at 30 gigahertz. So I said the 3 dB bandwidth was 35 gigahertz, but already at the 30 gigahertz, I'm having a hit on the distortion that's introduced because of the limited bandwidth. So there will be a homework assignment due at the end of the semester. The idea is to create a pulse shape to be sent to the DAC. You will process the transmission captured by your pulse, and other homework assignments will help you develop the skills that you'll need to be able to do this final one. I said D, it should be C. So think about it. Though we're early in the class, we don't have a whole lot of baggage that we can bring to it, but still you can start thinking about, what's going on here. I have a device which can create 100 gigasamples per second, but it only has 35 gigahertz of bandwidth. Suppose I wanted to send 100 gigabits per second of a square pulse. So a square pulse is either a 0 or a 1. I have 100 samples. Suppose I turn each of those into just a 2-level signal. Well, then I'm sending something at 100 gigabits per second, and the occupied bandwidth is certainly going to be a lot more than 35 gigahertz. So what is happening with this DAC if I'm trying to push it so high. Okay, so that was a square pulse, and we'll see that shaping and equalization techniques are going to be able to help us attack this problem. So think about what the problem would be. What would the pulse actually look like if I use that strategy? And then we'll talk later about other kinds of strategies I could use with pre-equalization to compensate for that bandwidth of the DAC and some pulse shaping. And if you'd like to look about these concepts, you could look at some reading on, that is available on the website. So various manufacturers' application notes, and in particular also the spec sheet for the MICRAM DAC is available on the website for the course.